Hello everyone. Today we'll be continuing Module 3, Chebyshev filter. Analog low pass Chebyshev filter. There are two types of Chebyshev filters. Right. Now this is type 1 and this is type 2. Type 1 filters are all pole filters and they exhibit equiripple behavior in the pass band and a monotonic characteristic in the stop band. Whereas the type 2 Chebyshev filter contains both poles and zeros and it exhibits monotonic behavior in the pass band and equiripple behavior in the stop band. So this is the explanation for the type 1 and type 2. So let's start with the design of Chebyshev filter, wherein step 1 is from the given specification we need to find the order of the filter n. So here n is calculated by cos h inverse square root of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1 whole divided by cos h inverse omega s by omega t. The step 2 is wherein the value of n which we get, we need to round off the value of step 3. Using the following formulas, find the values of a and b, which are minor and major axes of the ellipse respectively. So these are the formulas to calculate the value of a and b, where in order to calculate mu, it is zeta dash to minus 1 plus square root of zeta dash to minus 2 plus 1. Once you find this value of mu, in order to calculate zeta, this is the formula square root of 10 to the power 0.1 alpha p minus 1 and substitute the value of zeta and you can find the value of mu. So wherein the omega is the pass band frequency, alpha p is the maximum allowable attenuation in the pass band, or it is a pass band attenuation also. So for normalized Chebyshev filter, omega p will be equal to 1 radian per second. Step 4. Calculate the poles of Chebyshev filter which lie on an ellipse by using the formulas. So sk is equal to a cos of phi k plus j into b of sin phi k, where the value of k is going to range from 1 to till n. So depending upon the value of n, the value of k will range. So in order to calculate the value of phi k, it is pi by 2 plus 2k minus 1 divided by 2n into pi. Again, the value of k is going to range from 1 to 2 till the value of n. After that, we will find the denominator polynomial of the transfer function using the poles. So by using these formulas, we will be calculating the denominator polynomial of the transfer function. Once we find the denominator, we need to find the numerator of the transfer function depending upon the value of n. Here there are two cases. If you find the value of n to be odd, then substitute the value of s is equal to 0 in the denominator polynomial and find the value. This value is equal to the numerator of the transfer function. Second step, for n which is even, then substitute s equal to 0 in the denominator polynomial and divide the result by square root of 1 plus beta square. Again, this value is equal to the numerator. Let's start with the problem. Given the specification, alpha is equal to 3 dB, that is the pass band attenuation. Alpha is 60 dB, which is the stop band attenuation. Fp, that is the frequency of the pass band, is 1 kHz. Fs is equal to 2 kHz, that is the stop band frequency. Now determine the order of the filter using Chebyshev approximation and find h of s. Here the value of omega p omega s are in kilohertz, but the value of omega p omega s will be in terms of radians per second. So omega p is 2 pi fp. So substitute the value of fp as 1 kilohertz. So when you substitute the value, you get the answer as 6282 radians per second. Similarly, in order to calculate omega s, substitute the value of fs as 2000 and you get the value as 12,564 radians per second. Now using these values and using the value of alpha p and alpha s, substitute these values in the order n, as the first step is to find the order of the filter n. So this is a formula. Substitute the value of alpha s, alpha p, omega s and omega p. We find the answer as 1.91. The second step is to round off the value of n to the next higher integer. So the value of n will be 2 now. Step 2, round off n to the next higher integer where we get n as 2. Now we need to find the values of minor and major axis. So mu is equal to zeta raised to minus 1 plus square root of 1 plus zeta raised to minus 2. So in order to calculate zeta, the formula is zeta is equal to 10 raised to 0.1 alpha p minus 1 to the power 0.5. And we get the answer as 0.99, or we can keep it as 1 also. So in order to calculate mu, I have taken the value of zeta as 0.99 and I get the answer as 2.431. Now we need to calculate the value of A and B. A is equal to omega p into mu raised to 1 by n minus mu raised to minus 1 by n divided by 2. So value of omega p is 6282, substitute the value of omega and we get the answer as 2848.88. Similarly, calculate the value of p and we get the answer as 6888.21. Step 4, we need to calculate the poles now. So in order to calculate the poles, this is a formula. Sk is equal to a of cos phi k plus j b sin phi k. And in order to calculate phi k, again this is a formula. Phi k is equal to pi by 2 plus 2k minus 1 by 2 1 into pi. Again the value of k for both would range from k till the value of n. As the value of n is 2 here, so we take the value of k as 1 and 2. So we need to calculate the value of S1 and S2 only. So if you substitute the value of n is k is equal to 1, so phi 1 will get as 135 and the value of S1 will be minus 2014.46 plus j of 4870.70. Here the value of a which we have calculated from the step 3 and the value of b which we have calculated from step 3. Substitute these values and calculate the value of S1. Here the value of phi 2 will be 225 degree. Again take the values of a and b from step 3, substitute here and we get the answer as minus 2014.46 minus of j 4870.70. Now we need to calculate the denominator of h of s here. So s minus s1 into s minus s2. So this is nothing but as a minus b plus a minus b into a plus b, which is a square minus b square. So if you substitute the value of S1, this will be S plus 2014.46 minus of J 4870.70. Similarly, if you substitute the value of S2 over here, this will be S plus 2014.46 plus J of 4870.7. So you can observe from the equations of S1 and S2. So this is representing as nothing but your A minus B and A plus B. So when you get the formula as a square minus b square, we get this denominator, that is s plus 2014.46 the whole square plus 4870.70 square. Now we need to find the value for the numerator. So there are two conditions if you get the value of n as even or odd. As the value of n is even here, we are going to substitute the value of s is equal to 0 in the denominator polynomial what we have found, and we are going to divide that result by square root of 1 plus zeta square. So substitute the value of s is equal to 0 in step 5 and we get the answer as 19.74 to the into 10 to the power 6. Now this is your numerator function value. Therefore the transfer function is h of s is equal to 19.74 into 10 to the power 6 divided by s plus 2014.46 the whole square plus 4870.70 whole square. So this is how you have to solve the problem. And again in the last step of step 6, you need to simplify the denominator of h of s and get the solution. A new problem here: obtain an analog Chebyshev filter transfer function that satisfies the constant. So this is a statement which we have seen in Butterworth filter. So this, when you get this kind of statement, this value will be representing your alpha p, and to this will be representing your omega p, this part. and this will represent your alpha s, and this will represent your omega s. But alpha p is what? 1 by square root of 1 plus zeta square. This is not the direct value of alpha p. We need to calculate alpha p is equal to 1 divided by square root of 1 plus zeta square, wherein 1 plus 1 divided by square root of 1 plus zeta square is equal to 1 by 2, as the value of alpha p is 1 by 2, and we get the value of zeta as 1. Similarly, we need to calculate the value of lambda, wherein the value of alpha s is 1 divided by square root of 1 plus lambda square, and we get the value of lambda as 9.95. We have seen this problem kind of solution in Butterworth filter, so kindly refer that. So here the value of omega p is 2 and omega s is 4. Substitute the values in this and we get the answer as n is equal to 2.269. Second step is to round off the n to the next higher integer and we get n is equal to 3. So in step 3 we need to find the value of a and b. So we have seen the formula for mu, a and b, and we have seen how do you substitute and we get the answer. So this is how you get the value of mu and the value of a and b. Now in order to calculate the folds of Chebyshev filter, we need to use the formula for phi k so that we can get the value of sk as sk is equal to a cos phi k plus j b sin phi k. So here the value of n is 3. So the value of k is going to range from 1 to 3. So phi 1 is 120 degree, phi 2 is 180 degree, phi 3 is 240 degree. Substitute these values. Substitute the value of a as 0.596. Substitute the value of b as 2.087. So first value is phi 1 is 120 and we get this answer. Right. So similarly, we are going to calculate S2 and S3 here. So here you can observe that we have in the denominator we will be having S minus S1 into S minus S2 into S minus S3. Right. Let's see. In step 5, we will be calculating the denominator polynomial which is given by. So this is S plus 0.596 into S plus 0.298 minus of j 1.803 into S plus 0.298 plus j of 1.803. So this part is applied by a minus b. This is a, this is b. Again, this is a, this is b. So a minus b into a plus b will we get this answer. So this is your denominator now. Now in step 6, we need to find the value of numerator. Here the value of n is odd now. So we'll be substituting s equal to 0 in the denominator polynomial. So once we substitute the value of s equal to 0 in the denominator polynomial, we get h of s as 2. That is the numerator value as 2. Therefore, the transfer function of the Chebyshev filter will be given by h of s equal to 2 divided by the denominator answer. A similar kind of problem wherein we need to calculate the order and the folds of type 1 low pass Chebyshev filter. So this is how the flow is. Kindly refer. Comparison between Butterworth filter and Chebyshev filter. The magnitude response of the Butterworth filter decreases monotonically as the frequency omega is going to increase from 0 to infinity. Whereas the response of the Chebyshev filter is going to exhibit ripples in the pass band or a stop band according to the type. So in case of type 1, we have ripples in the pass band and we have a monotonic response in the stop band. In case of type 2 filter, Chebyshev filter, in pass band we have monotonic response and in stop band we have a ripples. Second point, the transition band is more in Butterworth filter when compared to the Chebyshev filter. So, the poles of the Butterworth filter lie on a circle, whereas the poles of the Chebyshev filter is going to lie on an ellipse. Now, for the same specification, the number of poles in the Butterworth are more when compared to the Chebyshev filter. That is, the order of the Chebyshev filter is less than that of the Butterworth. This is a great advantage because less number of discrete components will be necessary to construct the filter. Now we'll be looking at the frequency transformation in analog domain. So in previous session we have studied the design of low pass Butterworth filter and also the design of low pass Chebyshev filter. So the design of low pass Butterworth filter and Chebyshev filter are of normalized Butterworth filter and normalized Chebyshev filter. That is only for low pass. But we have different types of filter wherein we can convert that low pass to low pass, low pass to high pass, low pass to band pass, and low pass to band stop. So here there are four frequency transformation in analog domain. The first one is low pass to low pass transformation. So this is a normalized low pass filter which we have seen in solving the problem on Butterworth filter as well as Chebyshev filter. Okay. So if you after finding the transfer function h of s, will be substituting the value of s by omega c. That is the frequency transformation for low pass to low pass. Right. So here it is the same graph you can see for a Butterworth filter. So it is a monotonic characteristic. Now we'll be looking at low pass to high pass transformation. So given normalized low pass filter, it is desirable to have a high pass filter with cutoff frequency omega c. So here we'll be replacing s by omega c by s. So this is a low pass filter, this is your high pass filter figure. Right? Third one, low pass to band pass transformation. The transformation for converting a normalized low pass filter to a band pass filter with cutoff frequency omega L, that is the lower frequency, omega u, the upper frequency, can be accomplished by replacing s by s square plus omega L into omega u divided by s into omega u minus omega L. So here we'll be calculating the minimum value of omega. So minimum is of magnitude of A comma magnitude of B. Now to calculate the formula for A, it is minus omega 1 square plus omega L into u divided by omega 1 into omega u minus L. And B is equal to omega 2 square minus omega L into omega u divided by omega 2 into omega u minus omega L. So here again we'll be designing a low pass filter, then we'll be transforming that to a band pass transformation. Right. So here we have a low pass here. In this is a lower frequency and this is your upper frequency, omega 1 and omega 2. So in band pass, what happens is that in this band, in this part only, the signal can be passed. Now here there is a stop band. Here also there is a stop band. Low pass to band stop transformation. To convert a normalized low pass filter to band stop filter is given by s into omega u minus omega L divided by s square plus omega L into omega u. So again we have to calculate omega L. So in order to calculate omega, we have to calculate A and B individually. And depending upon the value of A and B, which is greater, then we have to take that value of omega L. We'll see with the problem here. For a given specification, alpha p is equal to 3 dB and alpha is equal to 15 dB. Omega p is 1000 radians per second, omega s is 500 radians per second. Design a high pass filter. So before designing a high pass filter, first before designing a normalized low pass filter, then use the suitable transformation to get the high pass filter. So here the specification which is given in the column is for a high pass filter. So this is a high pass filter figure wherein this part is a pass band and this is your stop band. So the pass band is of 1000 radians per second and the stop band is of 500 radians per second. But taking these specifications and design the low pass filter, then the value of omega p and omega s are going to change for a low pass filter. So the value of omega p for a low pass filter will be 500 radians per second and the value for omega s will be 1000 radians per second. The pass band, which is the low pass, here you can find the low pass filter wherein the pass band is for 500 radians per second and after that there is a stop band of 1000 radians per second. If you're designing a low pass filter, once you get the output of n and by taking the transfer function, you will be using a suitable transformation to get the high pass filter. So for the low pass filter specification, omega p is nothing but your cutoff frequency, that is 500 units per second. Omega s is 1000. Alpha p3, alpha is 15. So by using this formula of n, the order of the n, as we have seen for the last column, Butterworth as well as Chebyshev, so we'll be using this formula and we'll be substituting alpha p, alpha s, omega p, and omega s. So in order to calculate lambda, again we have a formula 10 to the power zero point 0.1 alpha s minus 1 square root. And again we have zeta. So after calculating lambda and zeta, we get 5.33, 5.533, and zeta is 1. And k is nothing but omega p by omega s. So which we get 0.5. It is 1 by 0.5. So therefore, the value of, by substituting the value of lambda, zeta, and k, we get the order n as 2.468. Now we'll be rounding off this to the next higher integer, that is 3. So the value of n becomes 3 now. Now h of s for omega c is equal to 1 radians per second and n is equal to 3. So for the order of n is equal to 3, this is the transfer function, that is s1 divided by s plus 1 into s square plus s plus 1. So for a normalized low pass Butterworth filter, the omega c will be equal to 1 radians per second, and for a normalized Chebyshev filter, omega p is equal to 1 radians per second. So once the transfer function has been found, now we have to find the high pass filter by using a suitable transfer function. So to get the high pass filter having cutoff frequency, so omega p will be 1000 radians per second now. As for converting low pass to high pass, we will be using omega c by s. So omega c is nothing but your pass band itself. So this 1000 by s, substitute s by 1000 by s, and we get the answer. So this is how we are going to convert that low pass to high pass. So we have a transfer function h of s equal to s1 divided by s square plus s plus 1, which is representing the low pass filter, and it has a pass band of 1 radians per second. That is this. That is a numerator value. Now using the frequency transformation, we need to find the transfer function of the following analog filters. First one, a low pass filter with a pass band of 10 radians per second. So we need to convert low pass to low pass. If it is high pass, we again need to convert the low pass to high pass. Right. So in a similar way, first one is a low pass filter with a pass band of 10 radians per second. So low pass to low pass transformation is S divided by omega c. So the value of omega c is nothing but 10. Pass band, that is pass band omega p is equal to omega c for a low pass filter. Substitute the value of omega c as 10 and substitute the value of s in terms of s by 10 in the transfer function of h of s, and we get the answer as 100 divided by s square plus 10s plus 100. Next, now we'll be looking at the transformation for low pass to high pass transformation. So a high pass filter with a cutoff frequency of 1 radians per second. So here the value of omega c is 1. Right? So again you're going to replace the s by 1 by s in a transfer function h of s, and we get the answer as s square divided by s square plus s plus 1. The third one, high pass filter with a cutoff frequency of 10 radians per second. So the transformation for low pass to high pass is omega c by s. So the value of omega s is 10. So 10 by s is replaced in the transfer function, and we get the answer as s square divided by s square plus 10s plus 100. Low pass to band pass transformation. So for the transformation for low pass to band pass, we'll be using this formula. Here, omega u into omega l is nothing but omega naught square, and omega u minus omega l is nothing but b naught. So omega naught can be written as square root of omega u into omega l, which is the center frequency of the band pass filter. And omega b naught is equal to omega u minus omega l is the width of the pass band. Right. So this is, so now we'll look at the problem, then we can understand which is center frequency and which is width of the pass band. a band pass filter with a pass band of 10 radians per second and a center frequency of 100 radians per second. Right. So here, center frequency will be 100 radians per second. That is omega naught value. Now, and the pass band of 10 radians per second is nothing but your bandwidth or width of the pass band. That is the value of V naught, which is equal to 10 radians per second. So substituting the value of omega naught. So the value of omega naught is 100. So as we are replacing this by omega naught square. But the formula is omega naught is equal to square root of omega L into omega U. So hope you can understand why we are taking it as square. Substitute the value of omega naught as 100 and the value of V naught as 10. Now take that transformation and replace S by S square plus 100 square divided by 10. Substitute these values here and solve accordingly, and you get the answer as 100 S square divided by S raised to 4 plus 10 S cube plus 20,000 S square plus 10 raised to 5 S plus 10 raised to 8. So now low pass to band stop transformation. S is replaced by S into omega U minus omega L divided by S square plus omega U into omega L. So here V naught is equal to omega U minus omega L, which is width of the stop band now, and omega U into omega L will be equal to omega naught square, that is the center frequency. Now the question is a band stop filter with a stop band of 2 radians per second and a center frequency of 10 radians per second. So this term, the numerator is V naught, that is the stop band, width of the stop band, which is 2 now. And this omega naught, omega U into omega L is equal to omega naught square. So the center frequency is 10. So that will be 10 square. So you are going to substitute S by 2S divided by S square plus 100 in the transfer function, and we get this answer as S square plus 100 the whole square divided by S raised to 4 plus 2S cube plus 2014 S cube plus 200 S plus 10 raised to 4. Thank you.